Okay. So we will talk about these exercise questions in lecture 8 about the Laplace transform. So there is a table of Laplace transform. Okay. And all our computation would be based on the table of Laplace transform. You don't use the basic definition, instead you use the table. So the table of Laplace transform is on the lecture note in lecture 8. There are 37 formulas in the table of Laplace transform. If you have a lecture note, you can find the 37 formulas. Okay. And there are many properties of Laplace transform which help you to calculate these results. If the function is not on the table, you use the property of Laplace transform to reduce the function into a simpler function, which you can find on the table. Okay. For this, it's already on the table. For this question, if you look at item 10 in the table, okay, you look at this table, you use the formula 10. And it says that the Laplace transform of this function, it directly tells you the result. Okay. If you have the table, you can look at the formula 10. Directly tell you the result. Okay. But for this cosine square, you don't find it in the table. So you have to reduce it to some simpler functions by using trigonometric identity. You know that cosine square of t equals 1 plus cosine 2t divided by 2. So now you remove the square, no such square here. If there is no square, you can use Laplace transform. You can find this on the table. So it's according to linearity, you can extract this. You can extract this half. Initially, you have a Laplace transform of half plus Laplace transform of half cosine 2t, but you can extract this half outside. So you have Laplace transform of 1, the Laplace transform of cosine 2t. Okay. For these two functions, you can find on the table. For example, Laplace transform of 1 is 1 over s. And the Laplace transform of cosine 2t is formula 8 on the table. Okay, so this is the formula 1. And this is formula 8. Okay. So this is the basic idea. If this function is not directly on the table, you should convert it to some simpler function which you can find on the table. Okay. Now, what if we multiply the function by an additional exponential function? Well, this requires you to use a property. The property is also written on the table. If you look at the table, you find the formula 29. So formula 29 says that if you multiply a function by an exponential function, then the Laplace transform of this is the Laplace transform of this original function f. You transform f into a function. So suppose this function is fs. Then you shift this s by c, by the constant c in the power of the exponential function. So according to this formula, if we put cosine square of t here, the Laplace transform would be this function. So for cosine square of t, you have this result. This is its Laplace transform. So let's put this result here. Now we need to replace s by s minus c in this result. So let's replace s by s minus c. c is 1. In this question, the constant here is 1. Okay, this is your c. So here c is 1 for this question. So you replace all the s by s minus 1. You see, this is s minus 1 square plus 4. So this is the answer. Okay. So we learned this property, but this property actually is on the table. So you can find it on the table. Okay. You should know there exists such a property. Then you look for this property on the table of Laplace transform. Okay. So now it comes a more complicated function. So this is 5t plus 2. So there is such a formula on the table, actually. If you look at the formula 15, you directly find the Laplace transform of this sine 5t plus 2. You find this result. So this is sine 2 s here plus 5 cosine 2. So this should be 25, okay, according to formula 15. So you should look at your table of Laplace transform now. Okay. Open this table, open your lecture note and find this table. then you can find this result. Okay, so but there is an additional exponential function. Okay, so in the table there is no such exponential function. So we need to use formula 29 again. If you add an additional exponential function, then you should replace the s by s plus 1 in this question. Okay. That's it. So I would require you to write down the formula you use. Okay, when you do such questions, please write down which formula you use. Okay, because there are various different formulas. If you don't mention which formula you use, other people cannot understand what you write. So we also learned how to use Laplace transform to solve differential equation. Okay. So previous question is just about Laplace transform. Now we need to apply this technique to solve differential equations. And Laplace transform can be used to solve differential equations only when you provide the initial condition. Okay, because when you apply Laplace transform to such derivatives, you would need to use the initial condition. The formula contains such initial condition. So you can find the formula also on the table of Laplace transform. For example, you can formula 35. It says that 35, it says that if you apply the Laplace transform to a derivative, then you get the Laplace transform of y multiplying s minus y0, the initial condition. Okay. And the formula 36 tells you similar result if you apply Laplace transform to second order derivative. Then you would get s squared times capital Y. Capital Y is the Laplace transform of small y minus s times y0 minus y prime 0. Okay. So for this question, it's easy because the initial condition are 0, so you wouldn't have these low order terms. This is for this question. Okay. So now you apply this Laplace transform to the whole equation. So you get 3 times s squared plus s minus 2 on the left side. On the right side, you get the Laplace transform of t, which is 1 over s squared. Okay. So if you apply Laplace transform to the equation, you immediately get this result. From this result, you can solve what is your capital Y. You solve that capital Y is s squared, 1 over s squared times this. So this can be actually further factorized. It can be factorized as 3s minus 2 times s plus 1. Okay. You see that there are three factors. There are three factors. Okay. So let's temporarily don't omit this part, 1 over s squared. Because we have a formula. If you divide s squared in the Laplace transform, when you take inverse Laplace transform, you only need to compute two integrals, actually. So let's only focus on this part. This part is contains two factors in the denominator, and we can decompose it into two parts. Each part contains only one factor. So let's say we decompose it into these two parts. So each part contains only one factor in the denominator. The question is determine what is A and B. Okay. So let's determine what is A and B. So we require that the sum of these two terms should be equal to the original term. Okay. And if you sum up these two terms, initially you would get Initially you would get A times s plus 1 plus B times 3s minus 2. You would get this, but you hope that this can be equal to this. Okay. So this means that A, if you collect the coefficient of s and the constant part, the left side would be this, and this should be equal to 1. Okay. If this equals 1, then you require a plus 3b to be 0 and a minus 2b to be 1. You require this, and you can solve A and B. So what is A? What is B? You can solve that A should be 3 over 5. B should be minus 1 over 5. You can verify this. Okay. So once you have A and B, now you have this A and B, you know how to decompose this function into simpler functions. Then you apply the inverse Laplace transform to capital Y. Okay. So now you know that capital Y is just 1 over s squared times A times this term. If we divide 3 in both upper and lower side, we get this. Okay. Plus B This is B. So both A and B contains 1 over 5. We can extract this 1 over 5 outside the bracket. So this is your capital Y. And if you apply the inverse Laplace transform, let's first focus on the interior part. The inverse Laplace transform of the number of the function inside the bracket can be easily found. This is just the exponential 2 over 3 times t minus exponential minus t. So you can find this in the table of Laplace transform. So this is formula 2 just. In the table of Laplace transform, this is formula 2, which tells you that Laplace transform of exponential function is just 1 over s minus something. Now you know the Laplace transform of the function inside the bracket. Outside the bracket, there is a 1 over x squared. Okay. So the inverse Laplace transform of a function divided by s squared is just a double integral. Okay. So you just need to integrate twice from 0 to the current variable. Every time it's from 0 to t. Okay. So for which function? For this function. Divided by 5. Okay. There is a 1 over 5 here. So this 1 over 5 comes from here. You have 1 over 5. So let's use a different notation, sigma, because we first integrate sigma from 0 to tau, then integrate tau from 0 to t, then you get a function of t. So anyway, you need to integrate it twice because of this s squared. It gives 1 over s corresponds to an integral, while 1 over s squared corresponds to 2 integrals. So if you can integrate it twice, you get the result. So the integral can be easily computed, actually. If you integrate a function of sigma, you simply get an antiderivative of this function. This minus 1. Okay. And integral of the second function of the exponential minus sigma, you get a plus. It's this. Okay. Then you need to integrate this function again from 0 to t. Okay, so you integrate it again, you would get the results. I would directly write down the result for you. So you should check this step. Okay. Well, on yesterday's video, there is a formula. If you attended yesterday's lecture, in the video there is a formula. Okay, so I will upload that formula into the new lecture note and upload the new lecture note to the Blackboard system. So now I attached a table of Laplace transform in the Blackboard system. I also uploaded the Laplace transform table here into the Zoom. If you look at the chat of this Zoom, you can find this Laplace transform table. Okay, so it's also in the Blackboard system now. Okay. So in this table, you can find a lot of such formula. For example, you can find formula 35, 36. These are quite useful. Okay, just 35 and 36. You need to frequently use formula 35, formula 36 when you solve differential equations, especially. Okay. So here we also need to use formula 36. Every time we write down this, the Laplace transform of a double derivative is s squared times the Laplace transform minus s y0 minus the derivative at 0. And for this question, derivative at 0 is 0, but the function value at 0 is 1. It's not 0 now. So you have an extra term minus s. Then apply the Laplace transform to the equation. You obtain s squared capital Y minus s minus y. Okay. Equals Laplace transform of cosine 2t. Well, cosine 2t, 2 times t is in formula 8. You should use formula 8 now. Okay. So now you solve capital Y. You find that capital Y satisfy an equation. And this is the equation. And then you divide the equation by the left side coefficient. Okay, you find capital Y. Then you apply the inverse Laplace transform. So you apply inverse Laplace transform to every term on the right side. It remains to calculate the inverse Laplace transform. Okay. So to this end, you need to decompose these functions into simpler functions, just like in the previous question. For example, you need to decompose these complicated functions into simpler functions, sum of simpler functions. So for example, every term contains only one factor. Okay, in total, there are 3 factors. There are ABCD, some constants for you to determine. Okay, then you determine ABCD. Okay, so this is left for you as an exercise. Okay. So let's focus on the next question about a new type of equation that you haven't learned in previous lecture. It's called differential integral equation. It contains both derivative and integral. Okay. So we haven't learned how to solve this type of equation before, but in this lecture, you know that it can be solved by Laplace transform. You just apply Laplace transform. Okay. You would need to use formula 35 again, which says that Laplace transform of derivative is S times this. While Laplace transform of integral would be the capital Y divided by S. Okay. So this is formula 32 actually. You need to also use a formula 32. Laplace transform of integral is simply capital Y divided by S. Right? So for formula 35, actually, initially you need to subtract from it the initial condition, but for this question, initial condition is 0, right? So you actually don't have this extra term. So anyway, by using these two formulas, for formula 32 and 35, you apply the Laplace transform. Apply the Laplace transform to the equation, you get it. So S times capital Y plus 1 over S times capital Y equals Laplace transform of T, which is 1 over S squared. Okay, here you use formula 3 actually. Okay, so you can solve capital Y. If you multiply S on both sides and divide the coefficient of capital Y, you get this. So you need to apply inverse Laplace transform to this function. But you know that inverse Laplace transform of this function is known. Oh, let's see. S squared plus 1 in the denominator. This is sine function, right? This is sine function. Okay. You can find this in the formula 7, I think. So there is an additional S here. With this additional S in denominator, it means an integral, okay, in the inverse Laplace transform. So inverse Laplace transform of this function divided by an additional S would be simply an integral of this sine function. And this would be negative cosine T minus 0. So it's this. So this is how we work out this type of questions. So you try to simplify the function that you want to perform inverse Laplace transform. Initially, you get a very complicated function, but you only need to find the inverse Laplace transform of this simpler function, right? Because this additional S, you can view it as an integral, okay, in the inverse Laplace transform. Okay. So why? This is simply formula 32 actually. So this is formula 32. You see that you used a lot of formulas in this single question. Okay, you use the formula 32 here because formula 32 says that if you apply Laplace transform to an integral, you get 1 over S. Okay, so now you have this 1 over S. You apply inverse Laplace transform, you get an integral. So you use the formula 35, 32, formula 3, 7, and then 32 again. Okay. So this shows you the importance of this Laplace transform table. Okay. So this is a similar question. similar integral differential equation. So we will not consider this. We omit it because it's similar. Okay. The only difference is that you have an initial condition. So therefore, you would have an extra term here, but that doesn't affect your subsequent calculation. Okay. So instead, in addition to the solving a single equation, you can also solve system equations by using Laplace transform. But I wouldn't recommend you to use this Laplace transform technique in exam, because for system equation, you already know one way to solve such a question, right? In the previous lecture, you know that you can combine the two equations and reduce the system to a single equation, and then you can solve it. Okay? So by using Laplace transform, you can also solve it, but it requires you to compute very complicated functions, very complicated inverse Laplace transform of very complicated function. That it is easy to make mistakes. Okay, although the two methods both lead to the same solution, the technique of using Laplace transform for system equation seems to be very complicated. Okay, I would recommend you to use the technique in the previous lecture for such type of questions. Okay, so that's all for today's tutorial session. If you have questions, you can ask. And about the exam date, it's not announced so far. Okay, so I will let you know exam date after it is announced. Probably the exam will be in May. Oh, May the 14th, it's already known. Okay. Any questions? If there were no question, so let's meet next week in class time. Okay. Thank you for coming to the tutorial session today. So see you next week.